Hi, in this video we will discuss LeetCode problem 2192. What is the problem name? Problem is all ancestors of a node in a directed acyclic graph. Okay, so you all know what is directed acyclic graph. Directed acyclic graph, DAG. Directed means there will be direction, like it will be go to U to V or V to U, not bidirectional. What does it mean? You can go to U to V and also you can come back from V to U. But directional means you can only go to U to V, not you can come back from V to U. Okay. Acyclic means there is no cycle. Acyclic, like this is not possible in this way. There should be any cycle, no cycle. This is acyclic, cyclic. So there should be any cycle. Okay. In the graph, they are trying to mention this. Okay. So the problem statement, you are given a positive integer n representing the number of nodes of a directed acyclic graph DAG. The nodes are numbered from 0 to n minus 1. Okay. So there will be n nodes and node number will be from 0 to n minus 1. Okay. You are also given 2D integer array edges, where edges I means from to 2i. This is directed graph. So you can only go from to 2. Okay. There is an unidirectional. Okay, edge from I to 2i in the graph. Okay, so we have to return a list answer where answer I is the list of ancestors of the ith node sorted in ascending order. Got it? So what is the ancestor? So what is the ancestor? Ancestor, suppose this is one node direction. So this is another node. Suppose this is 0, 1, 2. So what is the ancestor? There is mentioned that a node U as ancestors of another node V if you can reach V by a set of edges. So ancestor means, suppose what is the ancestor of node 1? Like that, can 0 will be ancestor of 1? I have to check. How to check? If it is ancestor, then what is the, we can reach from U to V. Here U is 0. I can actually reach. I have to check. I can reach from node 0 to node 1 in any path. Okay, path, it does not matter. We can reach or not. Okay, so okay, I will check. Okay, this is one edge is there, so I can reach here. Okay, 1. So this is one answer. So 2 is an answer. 2 is an ancestor of node 1. Okay, let me check. Can I reach 2? Can I reach from 2 to 1? Okay, there is any edge from 2 to 1? No. So we can't reach, so this will not be an ancestor of 1. So for node 1, the ancestor will be only 0. Okay. For node 0, suppose, is it 1 possible? Can I reach 0 from 1? No, there is no edge from 1 to 0. So we can't reach. Okay. Any can 2 is a possible ancestor of node 0? So I have to check, is there any edge from 2 to 0? No, there is no edge. This is a unidirectional graph. So this is from 0 to 2, not 2 to 0. So there is no edge. So this is also not answer. So list of 0 will be empty. So then I have to check for node 2. Can 0 is a possible ancestor for node 2? Can I reach 2 from node 0? Yes, I can reach. There is an edge, right? So this is one possible answer. I have to check 1 is a possible ancestor of node 2. I have to check, is there any edge or path from node 1 to node 2? No, because there is no outgoing edge for node 1. So this is not an answer. Got it? So I have to return this way. So let's go to the example. So for this example, like for this graph, first of all check for node 0. Is it possible to go from 1 to 0? 1 to 0? No. We can go 1 to 3, then there is no edge from 3 to 0. So there is no path I can reach from 1 to 0, right? So this is not possible answer. So I have to check again 2 to 0. 2 is a possible ancestor of node 0. So 2 is starting from here. 2 to 4 I can go. 4 to 6 I can go. 6, then 6 I can't go any other node. So this is not possible answer. So 3. So 3 to 0 can I go? Any path is present? 3 I can only go 5 or 6 or 7, and 5 is there is no outgoing edge, 6 also there is no outgoing edge, 7 also there is no outgoing edge, so there is also not a answer. Next is 4 to 0. Each possible 4 is a ancestor of 0 or not. 4 here is 4. So here actually I can go from 4. If I start from 4 to I can go 6. 6 there is no outgoing edge, so we can't reach 0. So I have to check 5 to 0. 5 if I start from 5 is here. So okay, there is no outgoing edge, so I can't reach. 6 to 0. 6 here. So if I start from node 6, there is no outgoing edge, so I can't reach. Then 7 to 0. 7 if I start from 7, there is no outgoing edge, so we can't reach. Okay, in this actually I have to check. Okay, let's check another example. Suppose for 0 it is empty. Got it? It actually you can see for 0 index it is empty. Okay, now I have to suppose it is check. There is some answer here. 0, 1, 2, 3, 4, 5, 6. Okay, for 6 I have to check for 6. Okay, can I reach from 0 to 6? From 0 I start from here. 0, 3, 3 to 6. Yes, there is a path, right? This path, this path. If I take these two edge, so this is your possible answer. So 0 is an answer. Got it? Now can I reach? Can I start from 1 to 6? Can I reach? Okay, let me check. If I start from 1, I will visit this. Then I'll come here. Then so we can take this edge again. So this is our possible answer. So 1 will be here. But next is 2 to 6. 2 to 6. If I start from 2, then I will came here. Then from 4 can I reach 6? Yes. If by this edge I can actually reach. So this is our possible answer. So 2 will be here. Next is 3 to 6. 3. If I start from node 3, 3 to 6, there is this edge actually there already. So 3 will be here. Then 4 to 6. Is it possible any path present from node 4 to node 6? Node 4. If I start from node 4, this edge. So this is also our answer. Let's say 5 to 6. If I start from 5, there is no outgoing edge, so we can't reach. So 5 will be not a part of this list. And sister. So next is 6 to 6. This is not possible. 7 to 6. If I start from 7, there is no outgoing edge, so this will not a possible answer. So 7 is not an answer. Got it? In this actually. So you got the logic actually. How actually output actually we are getting the output, right? So first of all, actually, what I have to found, like one logic actually you can observe, like for this any graph, for this graph suppose. So suppose node 1, we want to find out what are the ancestor for node 1. Okay, so actually we can also if I reverse the edges actually. So for this, suppose we created another graph 0, 4, then it is 1, then this is 3, this is 2. Okay, so there is an edge from 0 to 1. So suppose 0 to 1 there is an edge, so I just reverse it. So it will be 1 to 0. Okay, so 0 to 4 there is an edge, so I just reverse from 4 to 0. Got it? Then this is reversed to 4 to 1, and this is also reversed to 4 to 2. Got it? And this is reversed to 2 to 1, and this is reversed to 2 to 0. Got it? Now 3 to 2 and 4 to 3 and 0 to 3, it will be converted to 3 to 0, and this is 1 to 3, so it will convert to 3 to 1. Got it? Now if I just reverse the edges, so I will get this graph actually. Okay, so if we find out that what is the ancestor of particular node 1, okay, any random node. So if we start from node 1, then if I start to visit, okay, then actually what will be the, if we start from node 1, then what will be the node actually I can visit from node 1. First of all, I can visit 1, then actually what is the edges, adjacent list of edges are there. This I can actually go to 0. Then from 0, can I go any higher, any other node? No, we can't go. So for this one, I can only go 1 and 0. We can only visit 1 and 0. Okay, so you can actually check that G1 is always, because we start from the current node, so it will always visit it. Now also you get another node 0, extra node. Extra node means different from the starting node. So this is your ancestor of 1, 0. So you can actually check for this 0 is an ancestor of 1. Yes, if we take this edge, we can actually reach from 0 to 1. So this is 0 is an ancestor of node 1. Got it? So if we just reverse the edges, so if so I will start from each node, each individual node, like from 0, then I will start. So for each node actually I will check which node actually I can reach if we start from the current node. That actually we can reversely actually we can actually, because if we can reach this node by reversing these edges, so actually I can actually come to this node by original edges. By reversing, if I can reach from here to here, so actually I am in what actually doing. If I visit the actual edges, so actually I will come to here actually from parent to child. This will actually parent, and this will actually child. Got it? So if I reverse it, then I am going to child to parent actually. This actually help us to actually where actually parent can come, right? So got the logic, right? So go to the code actually. So what actually I am doing, I am just creating the adjacency list. So I am just traversing the edges. Okay, I will get from and to. Okay, so what actually I am reversing the edges. So what actually I am storing for 2 actually I am storing from. So from U to V actually I am storing V to U. Got it? Now I have written the ancestor list. This is your answer. Got it? So I have created the adjacent list. Got it? With the reverse edges. Now I have created a variable for answer. Now what I am doing, I am starting from each node I. Okay. So I will check actually which node actually I can reach from starting from this node. So that's why I am starting from I is equal to 0, I less than n. There maximum n nodes are there. So I have taken ancestor. This is actually our current answer, current ancestor of the current node. Okay, and another set. This will actually check have I visited the current node whenever starting out to visit it. So I will check is there any node duplicate or not. Duplicate means visiting again or not. So is it possible, right? So in this way I can actually go in this actually, like here also there is possible. So this will not only visited twice. Got it? So just there for this handling actually I have taken this visited array, visited set, so it actually store which node actually I am currently visiting. Okay, so and I am starting the DFS, calling the DFS function. What actually passing the current node, starting node, and the adjacency list. This actually give the reverse edges, and the visited. This actually store the handle the duplicacy. Okay. Now after getting after this actually I got the visited. This what actually this will store. This will store all the nodes which actually are we can actually visit if I start from the current node I. Okay. So I am just I'll just traversing. I will check the in node. I'll check always it will be visited node will die. Node will be I, it will always visit because you are starting from the current node. So else any other node actually I will check it is present on the visited node or not, visited set or not. So it is present means what? Actually we can reach like any node. You are starting from this. So suppose this is A, B, C. So we start from A. So what will be our visited set? Visited set will be A, B, C. It will contain A, B, C. So A will not be a ancestor because this is the current node. So I will check actually I have reversed this edges. So this will be our actually parent. B actually what is our edges? Actually what edges was this, like this is actually original edge. This is actually original edge. So if I reach A to B, then actually what happens? B can actually come to A. B can reach actually A. So B will our ancestor. So that's why I am traversing each and I am checking is this current node is present on the visited set or not. If it is present means this is our ancestor. So I will add this current node to our ancestor, current ancestor. Okay, after traversing, after checking all n nodes, I will add the ancestor vector to our answer. Okay, and at the end return the ancestor list. This is our answer. So I have called one DFS function here. They actually visiting, trying to visit all the nodes we can reach if we start from the current node. Okay, current node I. So I'm calling the DFS function by passing current node and the adjacency list and the visited node. Okay. So first of all, I will add the current node into our visited set. Visited node insert current node. Okay. Then I will check what is the neighbor node of the current node. Okay. So how should I will get? I will just traversing the iterating the node of each node of adjacency list of current node. What should I will get from U? I will get A, B, C. Suppose. So first of all, I will check A is present. I visited the current node. Current node means A before. If it's not visited, so it will not present in the set. Visit node if not find the current node, this neighbor is not equal to end, means this is not yet visited. So I will just visit this. Okay, I am passing the current here at the current node. I will pass the neighbor and the adjacency list and the visited node. Oh, got it. So in this actually we will do all the DFS and also the node which I can reach. Got it. And in the visited set actually I will store also all the nodes. Got it. Got it, right? So what is the time velocity of this? Time velocity means what is the time velocity? Time velocity here actually I am traversing each node. It will be time velocity big of E. Here actually I am traversing N, and for each node I am maximum we can visit N nodes again, because DFS can visit N nodes maximum. So time velocity will be N of N plus here actually I am traversing again N, because I am checking each node is present or not. So here time velocity will be big of E for this big of E, and for this will be N, and for each node I am calling DFS function. So time velocity DFS function will be N, and also the after that, after completing of DFS call, I am checking each node that node is present or not in the visited set. So that's also take big of N. So time velocity will be total time velocity will be big of E plus big of N square here. Got it. So what is the time space complexity then? Space complexity means we are using anything adjacent list. So this will be big of N. Big of N, yes, this is okay. And any other thing we are using anything? Yeah. No, we are not using anything. So big of N. Got it. What is the logic also, right? And also I have explained what is DAG. DAG means Directed Acyclic Graph. And then actually I actually explained that how actually we are getting the output, expected output. And then I actually shared the code. Got it. And also at the end I actually calculated also time velocity and space complexity of this. Okay. Thank you.